Bakemosa. Because now
like they came for breakfast late.
because na nkurɔfoɔ ne ka sɛ de bi a yɛayɛ late nti mesi ɛnɛ yɛnyɛ late.
So what do you come for breakfast late?
Ɛnɛ wowɔ ankɔ breakfast.
The car was there early. That's why I got to know they came.
Came late. Okay. So it's done. Okay. Okay. And the train. Yeah, train. Okay. But you put let me know, why is it difficult for you to come and take breakfast at 7? Why is it difficult to come and take breakfast at 7? Yeah. What is it wearing? I sure you can tell it to do not 50% of everyone. How do you can come and take the classes? You know, because this time I saw him come at 7. I'm joining the 7 to stay. The one he didn't want to come and take. He didn't want to come and take. Yeah? And well, I said that he didn't want the breakfast, that's how you do. I don't know. So how about you? Like if you come, you don't want to. Yeah, don't look for it. He like so what is not to do, not I just saw we don't want that to pass the other kids. No. I always come to the problem. What's the problem? Is it the time? 7 is 12. So 17 is like you have to tell people about something. Like I'm forcing you to come. It's like my first is your facilitators are saying that they are always things. Like you know, like, so you have to either we decide to cancel it or maybe push every other 7. I don't know. But the bad not about to be about to that 7 minutes. But I did out of 7:30, very much the less about 5 minutes. But oh, that's what I did for that was from now. It's like around our yeah, really no good plans, but that's not. Uh, then you just yes, for me.
Hello, hello. Bana.
Language, then we talk about yeah, that's yes, yes, I'm not. So let's see, we start that. Well, they are still up. We transfer that. I don't think so the last one there, and we should have come. But within the times. Every day, in Ghana, that explains the car about the plan. Ghana, so, Ghana, the one I'm the secret out some of the environment go out like this one supposed to be done, but our very wants to be trying to pass. So, but then yeah, the past coming from the how 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 I will tell you the past is moving from the future. Ah, which nature? So we start you find out here. So you can touch it. And then this is the board. If you want to write.
Before. Yeah, we can also give you an option of you writing on the screen.
Yeah, I want to try also. I mean, I like this better than this.
But we can do it. So when we focus primarily on it, and we can also prevent when you want to write, just do it.
Yeah, I try to write there, but can they read that in the last row? Can they read?
Please, can you see from the last row?
Four. You can't. They can't sit on the back.
Honestly, right.
Oh, no, but then they should come forward.
Sure, they all
Yeah,
come forward.
come forward. You can't see why at the back. All those at the back, please come forward.
So I must.
Right.
Come forward.
And I need to.
Let me get.
Max, Thomas.
Yeah.
Do come forward. You have to be right. That's it here. Please come forward. Come and do this. Those at the back, come forward, please.
But it doesn't matter. I can also write here on this thing.
Right there.
I'll try to write here. Why not?
If not, you use the marker.
Yeah.
Yeah.
No, that's always good. Please come forward because then I can talk to you. You know, we have to talk.
That's it here and all of that. That's it here as well. So, yeah. Yes.
Hey, one more question.
Yes.
I'll take how long. Yeah, now,
You want to write
I want to write and I want to use
the slide?
slide.
Okay.
Here's my
thing.
Okay.
So you have 3 fields, 1, 2, and 3. If you want more, I can give you.
Your start. You know, I mean, it's very difficult to say something in the short. So give me what I can say better.
Okay, I'll add 1 more.
No, not 3 is enough. let's stay with 3.
Oh, Professor,
Sorry, just add this.
you
Alright.
you have to join Zoom.
Zoom. Why can't I connect? It's impossible.
Yeah, it's possible you can connect, but then because you are doing live stream,
The pass.
you want everything to pass through Zoom.
How do I get in this Zoom link?
Yeah, so you just open Zoom, then we'll give you the meeting info. So we have the meeting ID.
Around 10:45 or probably 11. That means that if you need to the closing time, which is March, Saturday. So it's
My problem is I have to just connect to the
Wi-Fi.
Do you have anything else?
Yeah,
that
we
you
have
have?
Wi-Fi, go to other net.
the back on with the time. Other than our line will be, our server will be, and we'll try to go to the wholesale to
Ja, weiter machen, ja.
and set alarm and also in just one at a time.
Yeah.
And in Africa, know all of us, our lectures.
Instead of the looking his appointment.
So
Use the pointer.
I can point it, but it's not on the. So, and now we're unable to connect to Zoom. No, this thing is not yet on.
you are able to bring me and this one.
Yeah, it's trying. It's
Yeah.
trying to connect. Yeah, it's on. Okay, it's on. Now I get here. And how do I write?
Yeah, OneNote, you have whiteboard. You have, which one would you prefer?
You
use the whiteboard.
Yeah, I don't know them. It's not easy to write.
Yeah, you write with it.
So I'll send a book, and then we'll go. Whether breakfast or
Hello.
snack
Ooh.
during break time.
Okay.
Okay.
If
not
that one
ideal.
is not ideal, you can use OneNote.
What notes?
I'm opening OneNote.
Okay.
Alright,
So
so
go to draw.
I
Then
come
click
to your
any of the
lecture
pen.
want to be using the blackboard. Unfortunately, Ghana, we have
This one is
shifted from
I
blackboard.
think so. Huh?
Yeah.
So we try to see
Console.
whether the board, the one.
Yeah, yeah. You can use it.
So
So
remove the
when
white.
you come, you
Yeah.
come on, but yesterday.
So now I join meeting, right?
Yeah,
Yeah.
share screen.
Yeah, so what is the meeting ID?
This and.
Yeah, meeting ID. Meeting ID is here. Is it 915
And
584
584.
84.
So that's
Yeah.
And
the
now
password? You connect, you join. The password is 7571
yes,
62. Yeah.
yes. Great. Join.
Recording in progress.
Apart from that, there's I don't know whether I with your lecture.
Yeah, everything's
The
on.
Google.
I don't need the mic.
Yeah.
So now I share.
Press. Yeah, share.
Hopefully,
Show yourself.
you should get some assignment or some answer. Because
Okay, wait. Before I do that.
I mean, we are here to stay, we are here to know, we are here to learn. And so, that is why it's.
So will you be writing alongside?
That's why I really
If I am, no.
When you are done.
When I'm done, then I start.
And then you make them share the screen for me here. You stop sharing. They won't share the screen for me, so
Yeah,
right?
Are you here? or-
Yeah, yeah.
Hey, you
Just
must
draw-
tell me how you understand this. Are you physicists?
We are
Chemistry.
finishing mathematical statistics.
Yeah, you both must tell me whether I'm too slow, fast, or too difficult, too less difficult. Every day, I want to do something conceptual to get the people into the mood. And then later I do the calculations. But you must tell me, is it too easy or too difficult, or just right? Okay.
If I'm not here, I'm just motioning
That is
to
why
them. I'll give you feedback.
So you use of assignment.
I'm always in the office here, so don't worry. I'm also on the Zoom, monitoring
So
everything.
this time, what you look at the Google form or document and read the lecture. And study our applications because we need to know what we in terms of the lecture or happening. Whether there will be some modifications or something, then it wants us reshaping in all of that. So I don't want to waste time in spreading, and so we are fortunate to get someone from South Africa with one of the centers in South Africa, and he's definitely the one sharing that center as well. And he's in quantum sensing, biology, and communication. So let's give Thomas.
Thank you very much. Do I need a microphone or not?
No, I think you can talk without a microphone.
Can I talk like this? Do you hear me over there? using microphone.
Price, then it was fine, I don't know.
Yeah, but no, I like to have a mic.
You also have the management focus, it's give me the management.
Okay, so I just start by talking a little bit louder. I can't do that the whole time. And as Professor Martin said, I'm Thomas Conrad, and I'm from the Center for Quantum Computing and Technology. In fact, I'm the director of that center. And today I want to talk a little bit about quantum communication and quantum measurement. And I will do it first from a conceptual side, because you know the concepts are quite interesting, right? And I want you to come on board. And I will also ask you some questions. So always in pairs, look at your partner, find a partner next to you, and then I will ask you something. Okay? Just it's not difficult, and it's absolutely no problem if you don't know it and you don't get it. But it would be great if you start to think about things, you know. Then I've done my job. Basically, you have to understand it. No, I cannot understand it for you. You have to understand it. I can just tickle your brains. Okay, so I'm also from the university. Okay, I'm also from the University of KwaZulu-Natal. Right? This is a province in South Africa. It's actually in the east, below Mozambique, at the Indian Ocean. We have wonderful beaches. The water is 23 degrees, but I'm Huma pure Italian. You also have wonderful beaches, right? And your water temperature is higher, 30 degrees. So I cannot compete with that. But what I try to do today is to talk a little bit about quantum communication and measurement. Yeah, do we have it clicked or not? So, who knows what that symbol is? Anyone? Have you ever seen this symbol? What does it remind you of? What does it remind you of? The symbol. Of a model script. So some interesting script, yes. Something else?
We are looking at that.
Yes. If the IOIQ, what does IOIQ stand for? International Year of Quantum Science and Technology. And why do they have the symbol? It's like an electron that goes around the nucleus, right? In the old idea of how things are, you know, so that electrons go around the nucleus and go on. That's worse atomic one. You know, but it doesn't matter. So 2025 was the International Year of Quantum Science and Technology. Okay, so now this is the symbol of the university, right? Okay, now I try something, and you don't laugh, it's okay? I just try it. Nyansanpo Bosano Bajema. Did I say that correctly? Could you understand this? Who did understand this? Who understood it? No one? Oh, you don't speak that language? You do. So did you understand it?
Yes.
Thank you. All right. So it means, I looked it up on the internet, it means only the wise can tie the knot of wisdom. Right? It's not totally clear to me what it originally means, but I interpret it like this. You have to look at things in a wise way in order to understand them, in order to unlock the secret. Okay? And what I want to do today is I want you together to unlock the secret. Namely, what is this thing, quantum information and quantum technology? What is this about? Why can we not just do what we always did? Electronics and mechanics and also, why do we need quantum? And what does it give us? What is it good for? So that's the first thing I want to talk about, quantum information. What is information at all? What is quantum information? Then classical teleportation is a particular kind of teleportation. Okay, and I want you to understand this because it holds the key. Sorry, holds the key to the understanding of quantum technology. Strangely enough, and it is part of quantum communication. And then I talked a little bit about quantum measurement. All right. So this is what I want to do today. And let's see how far we get. But it's very important that you help because I cannot do this alone. No? And I hope that the people that are online can hear me. And I don't know where my microphone now is. They left me alone. Okay, then I just have to talk loud, right? Okay, so quantum technology, what is this? Microphone. Can I have the microphone? Okay, okay. So quantum technology has three different areas. The first is quantum sensing and imaging. You can imagine that if you take atoms, right, they are very small and they are very sensitive. The electrons that fly around them, they have spin, right? And spin means a magnetic moment. So, for example, they can measure like small sensors. They can measure an external magnetic field. If you flip them, right, in an external field, then the energy of the flip that you need for the flip depends on the external magnetic field. Because you know, if you are parallel with your magnetic dipole to the external field, then you need less energy as if you want to turn against it, right? So these electrons are these atoms are very good sensors for magnetic fields, for example, and we can measure magnetic fields up to an accuracy of 10 up to the -18 Tesla. Okay, -18. The record before we used cold atoms was at 10 up to the -15 with so-called squids, which have something to do with current, with currents that flow without resistance. And that was already kind of quantum mechanics, right? But quantum mechanics or quantum properties, so that means properties of atoms, they are kind of giving us much more meanings. Okay? In sensing, we understand that. Then in quantum computing, this whole workshop is about quantum computing, right? So quantum computing, enormous potential for computational power. We haven't realized it yet. And we need you, young minds, to help us. Because, you know, we've done our thing. I mean, we are not yet finished, but, you know, together we should start it because it's important. And I want to tell you that there is an alliance in Africa called, now it comes, the African Quantum Alliance. Okay? It's not a consortium, it's the African Quantum Alliance that has formed, and there are researchers from 6 countries so far from Africa, and we want to build a quantum computer. And it's not easy, but we don't care. We do it, okay? Because we think we can do it cheaper than everybody else. Because we know how to make a plan, okay? We can't afford all the fancy stuff. We just do the lowest stuff, you know, and that is good stuff. Sometimes it's better to have limitations, okay, and we have to use them. So that's quantum computing. Then we have quantum communication. That's what I will talk about. You see here is a bank and here ATMs, right? And there is like these lines, these curvy lines, and they mean basically electromagnetic waves, but more precisely single photons in our quantum system. And using these single photons, the ATMs can communicate with the bank securely, so that if you put in your PIN, no one can listen in and steal your PIN, right? Does anyone know how this is done so far? I mean, so far it's not done with quantum technology. How do you protect the PIN? Anyone knows that? Anyone knows that? How that works? RSA, exactly. Can I explain it? Okay, so it's like this. RSA is a public key encryption. So that means you have the public key. It's a pretty long number, okay? And you use that number to transform the PIN in some way. And then the transformed number you send to the bank, from the ATM sends it to the bank, all right? And then the bank, this is all done on the public channel, so everybody can listen in, right? But only if you know the prime factors of this big number, and usually there are only two. Only if you know these two prime factors, then you can decode the big number again, and you get the PIN, right? So it's a secrecy that is based on mathematical complexity. Namely, no one knows how to calculate the prime factors of a big number. And I want to tell you, there was a challenge called the RSA challenge. And they gave you a number with 250 digits. And when I saw that number, I wanted to take my pen and do it by hand. No, because I thought, come on, it was 150. No, how much money did I get? How much? 1 million euros if you find the prime factor, and you know it's only two. So you try, you know, trying is very, very cheap, because you know, we know how to multiply two numbers. It's very easy. You can do that in no time, you know, but somehow to find the factors is very difficult. And even though I found out, you know, of course I couldn't do it. I'm still standing here, so I didn't get the 1 million. So now the point is that with the new quantum computers, one of their strengths is exactly how to find the prime factors of a big number, right? For sure. And once that is true, all our encryptions, most of our encryption schemes are threatened. That means once we have quantum computers, and some people say, optimistic people like me say in 5 years, other people say in 10 years, right? Really pessimistic people say never. But once we have the quantum computer, let's say it's in 5 years, then suddenly all your encryption is worthless. People know how to decrypt. But that's not good. So at that point, there will be massive panic. You know, oh, we didn't know. Oh, what do we do now? You know? So we have to start now to think about these things, right? And how we can protect against it. And this one way to protect against it is this quantum communication. That's the communication with single photons or with some non-classical states of light. All right? And I want to talk a little bit about this later on, but first I want to talk a bit more about the concepts and about measurement. So this hour will probably be concepts, and next one will be measurement, and the third one will be communication. Okay, so I hope you're motivated, and we can start. So I will now start with something that I have shown before to the 10 people or 12 people that were at my course in January. And I want you, if you were there, who was there? Thank you, Ayla. And you must have, who else was there? Thank you, yeah. So don't get too bored. Think about, I want you to think about what you can criticize, okay? And tell me later. So
Basically, it's about, first of all, information theory. What is that, right? Classical information theory was developed in the 1940s. It started earlier, but really the basic concepts were found by Claude Shannon in the 1940s. And it works like this. You have a sender and you have a receiver and you have a signal between them, right? So basically it could be a radio wave, right? So now at some point the signal reaches the receiver and then there is messages, okay? And let's take the case there are 3 messages. Now, if we talk about information, we actually want to talk about the probability with which we expect the messages. Let's say I know the 3 messages. You know, I know already I know all 3 messages. Maybe the message is the weather will be fine today. It will rain today is the second message, and the third one, it will be cloudy. Let's say one of the 3 messages will come. Okay. But now, how much information is in the reception of the first message? If someone sends a message, the weather will be fine. What is the information in this? And in order to say that, I want to look at the probability with which I expect this. So in an environment where the sun shines always, the message, if the sun will shine today, you know, it's not so, we don't learn so much. Okay, it's not much information. So the smaller the probability is, the more information is in the message. Very strange concept of information. But let me go on and let me try to convince you about this. So how much information does A contain? I said the smaller the probability, the more information. And then I must write down the information method that now depends for the first information that is contained in the first message. Depends on the probability with which I, as the receiver, expect this message, right? So another thing is that if I get 2 messages, maybe the message A and B, our context makes no sense, but there are other contexts where this happens. So maybe in different days, first day I get message A, second day I get message B, then the probability for the joint event is the product of the probabilities, right? And of course, we want the information measure to be such that it is the sum of the information of the messages. If you send me 2 messages, I want that the information of the 2 messages is the information of the first message plus the information of the second. Right? This is what I want. If the messages are independent, send independently. So I want this thing here. And now, can anybody tell me which function you know where the product is mapped onto the sum of the functional value? So I have an argument product, which gives me the sum. Anyone has an idea how we should do that? Which function should we use? Okay. Yes. The logarithm. Okay, that's a good idea. The logarithm. Let's try that. Thank you. The logarithm. Okay, so let's say you make it like this. We said, you know, it must be such that the smaller the probability is, the higher the information. Right? That's why I take 1 over P1 for the information of message A1. But I want to take the logarithm in order to get the second property right. And we have clicker. And the second thing is then if I okay, so I should have written this down. Maybe I can write it down here in big letters. It didn't say so. So I want to get the second property, right?
So,
Different.
where's the eraser? We have an eraser. Fantastic. Okay, so I want to know, what is E of P1 times P2? All right, and I know that I define it like this: minus logarithm of P1 times P2, right, to the basis 2. We can talk about this basis 2 in a moment. Is equal to minus logarithm of P1 minus logarithm of P2. Yeah, I could also put here minus sign outside, and then I say here plus, if you like it. Right? Can you read that over there? Are you still there? No, the back row, I don't hear it. Hello. Thank you. Okay, so is that clear? Yes. So this means we can actually, go forward. We can actually write this down, and now we are going to calculate the average information that is in a set of possible messages with certain probabilities, right? And what is that average thing? So information is now the sum. And I have to take the logarithm of each message. So I'm now summing over all the possible messages. Let's say there are 3 messages. Then it was from 1 to 3. Thank you so much. No, it happened. Okay. Yeah. So the sum of pi to the basis 2, and then I have to put a pi here in front. Why is that? Because, if I want to have the average, I must also take into account with what probability does this occur as well, because if it has probability 0, then I can also leave it away, right? So some pi logarithm to the basis of pi. This expression is known as the Shannon entropy. And it's very important in classical information theory, right? And usually we call it with the letter H, Shannon entropy. Okay, very, very important. And when people understood this, they were suddenly able to calculate how much redundancy is in a message, and how much can I compress it. If I always say the same thing, I say twice the same sentence, that I don't need to tell you twice the same thing. So I can compress it and can just say one sentence, right? And in some interesting way, this thing here is the number of bits. Sorry, that's a mouse. Is the number of bits that I have, the average number of bits that I have to send if I want to send one of the 3 messages. Okay? Ideally, I totally compress it. Okay? And now, because we have such an abstract, we have such an abstract way of defining the information. We are actually in a good position. Why? Because we are not talking about the meaning of the message, right? The meaning of the message is something complicated. If you want to talk about meaning, then you have to probably talk also to the people in the humanities, right? They know more about meaning than us. And what is meaning? It's of course super interesting, but it gets super difficult. And it might also be subjective. You don't know what the meaning of the message. I mean, you might think it's a different meaning than I, right? So to talk just about the probability was a huge problem. To become so abstract was huge, you know, a huge, and sometimes it's good if you become abstract. So the information content does not depend on the meaning. Okay, there is one more thing that's quite abstract. Let me show you. So here is, can you see what this is? Do you know what that is? It's it's a storage medium, namely a magnetic storage medium. It's a hard drive. Okay, so magnetically stored information there. And I can transfer the information from my hard drive to my CPU, some electric signals that go around, without lost voltage, right? Then I can go and put it into the Ethernet cable or into optic fiber. And then I can send it via satellite as electromagnetic information, you know, waves, radio waves. And in the end, look what happens. What was on my hard drive was the information about this picture here, you know, this whole picture. And it appears exactly, no loss, no noise. You know, that is a big thing, right? So it means that the information can be transferred from one physical carrier to the next physical carrier without loss. That means we don't need physics for information theory. We can just do information theory and have no idea what the physics of the carrier, right? That is cool because, you know, the simpler it gets, the more things you can throw away, the more things you can forget, better for you, because you have more space to do the really interesting things, okay? So now, of course, one can ask, okay, so here's the summary. Information can be transferred without loss between different physical carriers. And the laws of information processing do not depend on the physical carrier. But what about quantum systems and information carriers? So let me show you one particular experiment. It's called classical teleportation. And it's part of quantum communication, right? But this is the key to everything, I think, my interpretation. Okay, so why is that the key? Well, first of all, what's going on here? So here I have a quantum system. That's the Kirby line, right? I just represent quantum systems as Kirby lines, and it goes into a machine that is called M. Okay, and this machine is a measurement machine. And what does a measurement machine do? Well, it takes some property of the quantum system and gives it a number. A number is classical information. You know, a number I can send via the telephone or via electromagnetic waves or whatever. So what this thing actually does is it produces a classical signal from the quantum signal. I can see the quantum system as a quantum signal. And now I transfer it via measurement to a classical signal. And then I send this signal to a preparation machine. And the preparation machine prepares the state of a second system, of a second quantum system, in such a way that we cannot, this was anticlimax. So this is the problem with all this clicking around. So to a second quantum system, and I want to prepare the second quantum system in such a way that no measurement can distinguish this system from this system. Of course, I mean no measurement. You can see it at a different location, right? So if you measure the position, you have already difference. But apart from that, I don't want any difference. It's properties. And when I talk about properties, I mean measurable properties. You know, I cannot talk about properties that I cannot measure in science. You know, we are empirical. Only what we measure exists for us. You know? We cannot talk about things that are not visible. We don't know. You know, that's a different part. Okay, so the quantum state is all the properties of this thing. And now the point is, if you could transfer the quantum information, so the information stored in the quantum system, to classical information in such a way that you can restore the quantum information without loss, then quantum information theory wouldn't exist. Why? Because we could do everything with classical information. Classical information theory, we saw everything is transferred from one physical carrier to the other without any loss. If this was lossless, if this would work without loss, quantum information theory would not exist. So we have strong reason to believe that it exists, otherwise they wouldn't have invited me. But we are not sure. So let me prove it. So I want to prove to you that it exists. I want to prove to you that you cannot do this without loss. Okay? And in the end, I will calculate together with you, hopefully, not today, but next hour, hopefully, I will show you how to calculate this. And that's a different thing. The first run, we do it just by thinking. In the second attempt, we do it by calculation. Okay? And I will show you a formula that you find in no textbook, and you can write papers. I've done it myself. And but we should share formulas. You know, some people keep their secrets quite close, and then you never know how they did this. You know, you read in the paper, oh yeah, it's easy to see. You know, it's not. You know, so that's the problem. But before I come to that, I want to show you this thing. Do you know what that is? Fax machine. You know what it is, but it doesn't exist anymore, does it? I mean, it's not used anymore. Okay, so this was a fax machine. Who doesn't know? Sorry that I asked this, but be correct. Who doesn't know? Who hasn't seen machine? Thank you. Good, very good. Yeah, absolutely. So you don't need to see it. It's not important anymore. But it used to be like this. Oh. It used to be like this. You had here some paper, all right, and you could actually put a paper with your writing in it. Then the thing would scan the writing on the paper. Then you dial a number. Here's a telephone. You dial a number. Take the telephone, dial a number, and on the other side it is the same machine. Okay, and that machine picks up, and then it has also white. The other machine has white paper. Here you actually put the original in, and it's scanned. The other machine of the receiver is white paper, and now it takes the information that was sent over the telephone line to reproduce, to print the original, okay, or a copy of it. So this is, this is the principle of a fax machine. And classical teleportation is working like a fax machine. Why? Because what we saw before, maybe let's go back. So what we saw before was like you put something in, you measure it. This is basically the piece of paper that you put into the fax machine. The measurement is the scanning of it. All right. So it looks where is the ink, how is it distributed on the paper. And then it sends it over the telephone line. That's the classical signal. All right. It sends it over the telephone line to a P, like printer. Okay. And that's in our case, I mean, in the general case, we call it preparation, of course, not printer. And then it reproduces the piece of paper. So while you can do that with a fax machine for classical information, you can't do it for quantum. Quantum information is now contained or carried by this quantum system. Okay, and in fact, it is identified with the state of the quantum system. So the collection of all its properties that can be measured, right? And it's not possible to, from a single copy, measure the state and then use that measurement to reproduce. Without loss, not possible. And that's why we have something really different than in classical information. We need a new theory, and it's called quantum information. All right? And what I want to do today with you is I want to go a little bit through the different machines that we can build with quantum information, or that we can build with quantum technology. These two are very close together. Then I want to also show you which machines we can't build. Okay, that's our goal today. But before I come to that, I just show you an example of quantum information, an example of a quantum system, and an example of a measurement of a quantum system, so that you understand why can't you measure, on a single code. Why can't you find the state on a single? Okay, so I try to do that, and I use the example of electromagnetic wave, and we know that electromagnetic waves can have quantum properties. Namely, if the energy, if you turn down the intensity until the energy becomes minimal, there is a minimal energy, and it's called, so that it corresponds to a photon. A photon is the elementary excitation of electromagnetic wave. Okay, so these are waves, and they can be excited to different degrees, and there is a smallest excitation, and that's called a photon. Okay, and if you look at the electromagnetic waves, who has seen electromagnetic waves before? Okay, is there anyone? I mean, but you heard of it, right? What is the most prominent example of electromagnetic waves that is around you all the time, at least during the day? Light, exactly. It's an electromagnetic wave, right? And in electromagnetic waves, you have an electric field that's oscillating like this, right? That's the red arrow. If you put some material there and you have some charges in the material, for example, antenna, then the charges also start oscillating, right? And this blue thing, anyone knows what that is? It's not electric field, it's the magnetic, electromagnetic waves, right? The magnetic field is always perpendicular to the electric field. It also oscillates. But for our purpose, we can just forget about it. Because if you know the electric field, you also know the magnetic waves. Okay, so now what is this? This is an interesting picture of two different directions in which the electric field can oscillate. So it can oscillate like a red wave in the y direction, okay? And it can oscillate like the blue wave in the x direction, okay? Now, if I superpose, so if I have these two directions at the same time, right? Then what happens is I get something else. I get, as you see here, this is just adding this vector and this vector. I get something that goes around like this, okay? And this is called the direction in which the electric field of electromagnetic wave is oscillating. Is called the polarization of the electromagnetic field. And this is called circular polarization because it goes around. All right, good. So, so let's look at the measurement of polarization. So how can we measure polarization? For example, one way of doing this, it is using a polarizing beam splitter. Okay, for a second. A polarizing beam splitter. Okay, in a polarizing beam splitter, the following happens. If the light is polarized in this direction, it goes through this glass cube which is actually two prisms that are put together, and in the middle, in the interface, there is a layer that only lets to polarization that is in this direction. Okay, if the polarization is vertical, if the polarization is horizontal, then it will reflect here. Okay, this is just a property of this material. Okay, and now we make these measurements, and of course, measurement means here I'm going to put a detector here, and I'm going to measure. Let's say this is a single photon. I'm going to measure, is the single photon coming into this detector? Answer: yes, it will come into this detector all of the time. Okay, so with probability 1. And if you do it this way and you put a detector here, then this detector will click all of the time. So it's not a problem to distinguish these orthogonal or perpendicular polarizations. You can do it. But what if I give you a polarization that is diagonal? Does anyone know how I can use diagonal polarization? As a superposition of vertical and horizontal. Look at this. I just superposed them. So these are the vectors, right? And now I do that at the same, they are synchronized, so when they are at the maximum, then both of them are at the maximum at the same time. And now I do this, right? And I ask you, what is the resulting polarization vector? So in each time, for example, this time I have to add this vector and this vector. I get this, right? Now look at this point. When I add them here, they are both 0. Okay, so I get this point, right? So I was here, now I'm here, and then I go like this, and I'm here. So I get diagonally polarized, right? Okay, so if I have such diagonally polarized light, here is 35 degrees angle, then what would I expect? Which detector should click? That's a good question. That's really maybe the most difficult question that we have. Let's first look at classical light. So if I have a light of a certain intensity, then I can expect that each detector measures half the intensity of the image. But what if I pull the intensity down, if I turn it down to a single photon? Then a single photon means it's an energy that cannot be divided. It's like an elementary particle. You cannot make 2 or no. So in order to click, the detector must get some energy from the path, or from the wave. But now, which detector will click? Yes. It's a probability, and what we say the probability is that the detector D1 clicks. It's a half. Why do you think it's a half? It's two possibilities, and one of which are looking at the Laplace rule, not cannot cite can someone help me? So günstig in my language, günstige Durchmöglich means the favored one, the number of favored ones divided the number of possible ones. One detector, 2 possible, 1 half. This is how we usually do it. And if you measure, it's really hard. Probability is half, but sometimes this detector fits, sometimes this, and normal nodes work. So if I only have 1 photon, and I want to say whether this photon was vertically polarized or vertically polarized or diagonally polarized, and I get a click in this detector, then I cannot decide, because in both cases it can happen. In the one case it happens with probability 1, in the other only with probability half, it can happen. So from a single photon, I can really not say, is it now vertically polarized or is it diagonally polarized? Or is it even horizontally polarized, the lower? So you see, there is something built in the nature of these things. It's highly strange because we don't talk about it. You cannot measure things. You cannot distinguish non-orthogonal sets. And we will do this in theory with formulas in the next hour. But at the moment, I just want to make a break because I think we need a break, right? What time is it? Okay, 9:31. Let's gather again at 9:12. Right? And then we can carry on. And I hope you are fresh. So best thing is go outside and run once around the building. Okay? I'm going outside and I will run once around it. Thank you. Something he might have.
I also don't know where the other mic is. That does.
We asked the technical guys to come away from it.
No problem. Okay. Okay, so we have to start. Or I want to start. It's 9:40.
As promised, we continue. And now, in the second period, I will.
Yeah, I really need the mic. So the guy here from the back.
Loud. All right, so I'll try to talk louder and slower because I talk too fast, and I'm sorry about that. I just talked to the people that assist us, and they asked me about the phrase that I said in the language. It's called tweet. Tweet in the language that tweet. And they said something to me. They said the phrase to me, but very fast. I didn't understand the word. So I can understand it if someone talks very fast in a different language. Yeah. So let's try to talk slowly and loudly. And you must, down in the back row, are you still there? You must tell me if you need it louder, or better even, come to the front. Then I don't have to do this. Okay, so I just wanted to say that we can send a superposition of vertical and horizontal, and we call that vertical 0. It encodes the number 0, and horizontal encodes the number 1. So that's like 1 bit. But we can also encode a superposition of vertical and horizontal, which is diagonal. And we call this a quantum bit. Because we can actually choose any direction in the plane, and even these, the circular polarized light, which you get if there is something like if they're an anti-sync, So when they are both the same, then you get diagonally polarized light. When they are an anti-sync, you start here. That means you start here. No, this is actually pi half phase shift. So you start here and you start down. Then this one goes to here, this one goes up, and you're here. So you went from here to there, and then you go back. No, you go like this. Yes. Now you are here. So I went from here to there, and I go wrong. You saw it. I cannot do it as good as the computers. All right, so this is called a quantum bit, a superposition of 0 and 1. And we could write 0 plus 1, but that doesn't help us because then everybody thinks this is 1, right? So we write it in a slightly different way. we write it with such angles, which are referred to as cats. This is a cat, and it basically means just a vector. It's a vector in a two-dimensional space here, two-dimensional complex space. But don't worry about it, in a two-dimensional space, and if I add two vectors, I get another vector. That's what vectors do, right? And this is a qubit, okay? And we can detect only 0 or 1, but not 0 plus 1. So if we really want to make a distinction between 0 and 0 plus 1, we cannot do it with certainty. Okay, so that's that. And with this introduction, I now want to talk about different machines of quantum technology, right? We saw here, we talked already about classical teleportation. And I want to talk now about other machines that we could construct if we had lossless classical teleportation. And I will show you a whole hierarchy of machines that does not exist. And the last machine is the most ridiculous of all. And so I hope we have some fun, okay? And then I come to the machines that we can do. And by doing this, by looking at machines that do not exist, we actually get a feeling for what this quantum technology actually cannot do. And then we look at what it can, all right? Maybe then we have a feeling for it. And maybe it brings new ideas. Okay, so let me do this on the board, the second part. And board means here, I will try something I've never tried before, and that is writing on the computer screen. I mean, yeah, I actually have never done that. Amazing. 20th century, 21st century. Okay. If you can give me that.
Yes, so you have this. Just online.
Yeah, give me. Okay.
Thank you.
Yeah. No problem. Okay, great. Okay, so I'll start with red. Okay, no, this is what I want. No, what's this? No, right. I know it. Oh, right. Okay, can I not scroll this way?
Or actually writes until it's finished, it comes to.
Okay. Good. So, okay. So first thing is impossible machines. Forgive my handwriting. I have to get used to this. Of QT, quantum technology. Okay, so there is a hierarchy. So the first thing is called classical teleportation. We just discussed it. It's not possible to do classical teleportation without loss. And I want to show you that this is not possible. So far, I just claimed this. This is a big writing. I hope you can read it. So now I'm going to scroll. Yeah, why can't I scroll? No, I can't scroll. Why does this everywhere? And I select. I don't want to select. I want to scroll. Let's see. You know how to do this? Yeah. I want to scroll. I want to scroll up. Yeah. Okay. Sorry for that. Must be nice. Yeah. Yeah, it doesn't work. Let me get that.
You're supposed to do the selects before you connect.
Select doesn't go. Okay, in the meantime, I talk further. What did you do? I'm in mouse, yeah. Mouse, okay, I can do the mouse, no problem. That's fine.
I just use the mouse.
Just need the mouse. Okay, that's fine.
No.
Can you go back? No, I need the thing back. Gone. Okay, possible machines. Okay. It's gonna be fine. Okay, so classical teleportation. I want to show you that that doesn't exist. And I do it by showing you a whole hierarchy of impossible machines. And the last one will be a machine where I can travel faster than the speed of light, and we don't believe it. Okay, so it's a classical, I reduce it to something absurd. Okay, so the second machine is a cloning machine. Cloning or copying, okay? I can also not copy quantum information. I think it's all too big. I have to write smaller. Sorry for this. So the third machine is simultaneous measurements of different observables. I will tell you later what that means. And the fourth machine is the Bell telephone. That is a telephone which you could make a phone call and transfer information faster than the speed of light. Of course, all these machines do not exist. And, you know, if it's true that if I can do classical teleportation, I can also do cloning. And if I can do cloning, I can also do simultaneous measurement. If I can do simultaneous measurements, I can also form faster than the speed of light. Then we believe that something must be wrong. It cannot have classical teleportation. It cannot exist. Okay, so it's a little bit of a philosophical argument, but it teaches you the concept. All right, so let's do this together. So I'm gonna draw the classical teleportation scheme, and then I will ask you to design a cloning machine. Okay, let me show you how I do this. I take the mouse. No, I take the mouse, yeah. And now I go to this this second part, clone. Okay. Okay, so a cloning machine does the following. It takes a quantum system that goes in, and here I have this cloner, and then two systems come out, and each of the systems cannot be distinguished in terms of measurements from the input state, from the input system. All right, so I basically copy the state of the input system on two other systems. Classically, I can do that think of my piece of paper that I put into the copying machine. It's called a copy machine for good reasons. It brings me another copy, and I have two pages. I start one, I have two. Quantum mechanically, this is not possible. This is an impossible machine. And because it's impossible, it's very good because we can invent something that is information that is sent, safe against eavesdropping. No one can copy the information. That also means it's very difficult to listen in and to make a copy of what you just sent. Right? So we can do secure communication, secure data transfer. All right, but I now need your help because you have to help me to construct this from this. So we assume that there is, I give you a classical teleportation machine. Assume the classical teleportation is possible without loss. Okay, that means I have some incoming signal, and then I make a measurement on that incoming signal. A measurement transfers the incoming quantum signal into a classical signal, and then I can re-prepare the initial state. Okay, so now you should use this. So here's the task. Use CT to build or to design copying, cloning, okay? And I give you a hint, and the hint is classical signals can be copied. Okay, so please, with your neighbor, okay, sit together, and I give you 3 minutes to discuss this and try to construct me this machine. Construct me this machine in terms of diagrams, just using this machine. And the property that classical signals can be copied. Design, okay? 3 minutes. It gives me explanation. Okay, okay, let's do this together. Yes. Let me just ask who got it? Who got a solution? Anyone? 1, 2, 3. Who got the solution? 4. Okay. Who didn't get the solution? Okay, maybe. Okay, didn't get the solution. Who doesn't care? Okay, so yeah. So maybe those that got the solution should tell us, and then do you want to paint it? Can you do it? Okay, just here on the computer. And then we discuss it, and those that didn't get the solution must say why this or whether they understand this or not.
Because we can copy the classical bits and we can initialize the classical bits. It's easy we do the cloning at the classical stage so that we can reinitialize them to our quantum system, the number of quantum systems that we have. So this is what I came up with.
Okay, must speak loud.
So since we want to clone the signal to many quantum systems, we can do that at the classical stage because we can reinitialize the classical stage, but we can't reinitialize the quantum state to multiple quantum systems. You understand? So let me draw this.
Yeah, best is to draw it, and then you see it. A picture says more than 1,000 words. Don't worry about it. Just go on, put the P there. Yes.
Yeah. So
That's it. Okay. Very good. Yeah, this is perfect. Do you allow me to explain it? Because I have a loud voice. Okay, thank you. Thank you so much. Can I have applause? So basically what happened here is there is a quantum state. So this is the quantum information stored in a quantum system, right? It cannot be copied or, sorry, usually cannot be copied. We are in the process of producing a cloner, a copier, a quantum copier, okay, and using classical teleportation. So what is happening here is we use the first stage of the classical teleportation machine, which is a measurement. A measurement transfers quantum information into classical, right? And then at this point, all the information is transferred into classical information. This is what we assume if we say that classical teleportation works without loss. That was the assumption. It's not true, but let's assume it for a moment to see where we land. And then we can take the classical information, put it into a copy machine or cloning machine. Cloning and copying means the same thing. And then I get twice the signal. Okay, the classical signal can be copied. And I was asked, what do you mean by copying the classical information? Do you mean that you have two devices, or that you have two carriers, or what do you mean? What does it physically mean? Well, physically it means that I really have two carriers. This is true. There must be two carriers, two electromagnetic signals, two radios. Okay? They both carry the information about the state of the system. So this could be some sequence of zeros and ones, bits. No, that's all we need. We can represent everything in bits, in classical information. We can digitize it. And then we represent it in bits. And here are the same bits as here, and they are sent to a preparation machine, which enable us to prepare the initial quantum state in two different signals, two quantum signals, right? So this whole thing here, from here to there, so if I look at this thing here, this whole machine, one thing goes in, and two systems come out that are each in the same state as the input system. And this is a cloner. Okay, this is classical here, classical cloner. But this would be a quantum clone. So we conclude that would we have a lossless classical teleportation machine, we also could construct easily a quantum clone. Do we agree with that? Are we happy? Who thinks otherwise? Who thinks it's not clear? Be courageous. Yes. Tell me what can you say? How far do you get? Where do you understand that